Okay, hello everyone. It is my great honor to host this special ICAX talks because today is a big day. This is Alice Zhang from Peking University. Uh, Everyone knows that we have a Thanksgiving party somewhere in the world, and some people's already gone for their parties. But today we also have a great news to announce for the Thanksgivings. Yeah, because yesterday we have this great news. Professor Jack Dish was one of our coordinators, co-organizers of ICANX, was elected to be the president of Australia Academy of Science. So that's really, really, really a great news. We celebrate for this, and congratulations to Professor Jack Dish. I think maybe all of you know him. I think every Friday, yeah, he is supporting this ICANX talks. He give us a big support because just now we discussed that. We say, every time we start our ICANX and the evening in Beijing, in Australia, already midnight. So Professor Jagdish always there. And Professor Jagdish was, ask questions, organize the sessions, and do a lot of, work for us. So great news. And thank you. And also, yeah, we hope Professor Jagdish leading the Australia Academy of Science going further, and also can, leading ICANX, go further and do more things. So that's all great news to share. And this Thanksgiving. And so we this week is last week of November. So in November we have four speakers. Three of them already on the stage. Today we are going to have the fourth one is Professor Zuankai Wang from City University of Hong Kong. So we will have our new moderators. Yeah, so as Professor Fu Lan from the same university as Professor Jagdish, and they are great colleagues, partners, and also Fu Lan was, I think, it's previous Professor Jagdish students. Yeah, so as our great pleasure and honor to welcome Fu Lan to join us. Yeah, Professor Fu, please.
Thank you very much, Alice. Good morning, good afternoon. No, I have not. Can you hear me? Okay, all right. Good morning, good afternoon, or good evening to the audience of ICANX Talks around the world. Welcome to the ICANN Talk Series 79. And as Alice introduced, my name is Lan Fu, and I am a professor in physics from the Australian National University. So today, we will firstly have 1 hour presentation from our distinguished speaker, Professor Zuankai Wang from City University of Hong Kong. And then we'll have half an hour panel discussion from an expert panel, Professor Anderson Shum, Professor Tia Li, and Dr. Ning Ying from Stanford. So at first, let me very briefly introduce our speaker tonight, Professor Zuankai Wang. So Professor Zuankai Wang is the chair professor in the Department of Mechanical Engineering, co-director of Center for Nature-Inspired Engineering, Associate Dean in the College of Engineering at the City University of Hong Kong. And he's a founding member of Young Academy of Science of Hong Kong. He has also won a lot of prestigious prizes, including the 2020 Explorer Prize, World Cultural Council Special Recognition Award, Outstanding Young Award from ISBE. Over the past 8 years, Professor Wang has published 18 papers in Nature, Science, or PENS series. So it's a very outstanding achievement. So tonight we'll be really hear Professor Wang talking about how to seek nature's principles and inspirations to rationally design novel surfaces to address the world's grand challenges such as water, energy, and health engineering. So Professor Wang, the floor is yours.
Thank you very much. Let me share the screen. Okay, good. Can you see the screen? Right. Okay,
yes.
Good. Okay, thank you very much, Professor Fu. And it's a surprise and honor for me to be invited by Professor Zhang to give the talk. It's my great pleasure. The title of my talk is Surprise on Surface. Let me start by asking a very, very simple question. What's your first impression on surface? Probably you think surface is very simple, right? Surface superficial, but actually surface are subtle as well. And the surface serve as armor to protect the material and also protect the device from being damaged. Surface are barrier to water and gas penetration, and also surface are barrier to contamination, and also surface are catalyst for many functions. And also surface are devil, as mentioned by Nobel Prize winner Pauling, God made the book, and the surface was invented by the devil. And also surface regulates the mass, momentum, and energy transfer. So now let's face surface and search surprise. When we try to search surprise, let's look at the history. Okay, so 2005 years ago, there's a very famous structural engineer. His name is Wang on a mountain. His hands was cut by a spiny needle in a leaf. The pain triggered him to invent a special cutting machine. I think all the Chinese people know that. 70 years ago, another man, his name is George, on his trip in a mountain, his hair and plant were covered by a burr from the burdock plant. This pain also triggered him to invent the vacuum tape. I think now it's widely used. So also 20 years ago, the shark skin inspired the people to win the gold medal in Olympic game. Okay, so lost the special and interesting surface in the world. Today, I would like to cover three special surfaces from weighting point of view. The first one is lotus leaf. The second one is getting acid and pitch plant. More importantly, I will focus on lotus leaf and pitch plant. Okay. I think many people, I think all the people know that lotus leaf can keep self-cleaning because on the rough surface, we have the air pocket. That's very good. But the problem is at a dynamic condition, the air pocket can be damaged. In that case, the superhydrophobic property is lost. On the other hand, pitch plant has very good self-cleaning property. But there's also some problem, for example, evaporation of the lubricant. Okay, so today I will try to answer some question in the surface science and engineering, especially from a scientific point of view. I want to discuss three questions. The first one is for hydrophobic surface. Usually, we want the liquid to leave the surface as soon as possible, right? If we define a physical parameter, we want the liquid to leave the surface with the smallest kind of time. On the hydrophilic surface, the liquid will spread, right? We keep our two parameters. The curve, right? The most important is you steer direction, right? To the left or to the right. And also the driving velocity, or the theme for liquid, right? The spreading velocity of liquid on hydrophilic surface. After answer the three fundamental questions, I will discuss some technical problems. For example, how to fabricate those kind of surface. Use very simple, powerful technique, and how to get power from the liquid, how to cool down the surface by special design, and how to explore the new functions. So let's first look at the history. Right, 200 years ago, the Thomas Young tells us on the surface, the contact angle is defined by the fabrication. And then when we modify the roughness, the contact angle was changed. Right? That can be described by Window equation and Casey equation, and then lotus leaf effect. And also we can fabricate a super hydrophobic surface based on hydrophilic surface. I also mentioned a slippery surface a few minutes ago, right? But for practical application, we really want the liquid to leave the surface as soon as possible. That is dynamic contact time. We want a short contact time because when time is shorter, the surface is more clean. We have better energy conversion, and also we have better heat transfer, and also we can prevent icing, right? But the problem is at the fundamental level, the time is constant. That work published in Nature, but if you look at the fundamental understanding, actually quite straightforward, right? When you play basketball, right, the basketball can rebound because basketball is elastic. The water is also elastic, right? The water has a surface tension. So the time here is constant. And especially 80% time is dissipated in the retraction stage. The water first spread, that is driven by inertia, is normal, and then the water will retract. 80% time is caused in the retraction. So probably now you want to find some material which can prevent retraction, because as I mentioned, 80% time is dissipated in the retraction stage, but it's difficult. Why? Because when the droplet reaches the maximum spreading, the droplet is like a pancake. Right? At this stage, the droplet is very, very flat, because the droplet won't come back to the original happy work. Even the droplet is anxious to come back to the original shape, but at this stage, the droplet is subject to the lateral force, right? Because the droplet is squeezed by into a pancake. The droplet have a large attraction force in the lateral direction. So if we can develop a new material, we can droplet jump at the end of the spreading. That will be cool. So how to do that? Can we design special material to produce large upward force? For example, if we can make the droplet to penetrate into the surface in such large deformation, we will produce large capillary force. If this force is large enough, probably the droplet can jump. To achieve that, we design the surface with large spacing. Over the past 20 years, people work on nanotechnology, right? They want to design tiny and tiny structure, but for that kind of surface, the water contact time always is constant. But in here, as shown in this movie, we reduce the time by 80%, right? So, for example, bird can finish 100-meter race by 9.58 seconds. But on our surface, we can finish 100-meter race by only 2 seconds. Probably in practical application, we don't have to use so special material, but this really represents a breakthrough, especially in our fundamental understanding. What's the shortest contact time between the liquid and the solid, right? So this phenomenon is not only occur in small scale, but also occur in large scale. For example, even large scale mechanical system, we still have this kind of pancake bouncing, right? So from this point of view, this phenomenon is universal, it's general. And also our work was recognized by Guinness World Record. So today I want to show you the story behind the work. When you look at the work, you find interesting, but there is a very, very interesting story behind. This work was done by my second PhD student, Yang Hua. Now he is a full professor in Dalian University of Technology. His background is agriculture. When he joined my lab, basically he didn't have any background in physics, no background in chemistry, no background in material. So after half a year passed, no any progress. I was not that sad. Actually, when I studied my PhD, I don't have any progress within the first 2 years, right? But still, I worry about his PhD thesis work, because in Hong Kong only 3 years. So I talked to Yang Hua. Probably the best strategy is start from something which is very, very simple. The most simple work is you put a droplet on the surface and then you observe droplet bouncing. That's what I did when I studied my PhD. So at that time, my first PhD student, Xue Mei, now she's the first professor in Nanjing University of Science and Technology. because at that time I don't have camera, I don't have funding, we don't have a good fabrication, but she may have the copper form, the structure is huge, right? If you look at spacing in more than 200 micron. So I asked Yahua to put a droplet on the super hydrophobic surface. My motivation is I just want to test whether Yahua can try very simple work. And one day, Yahua showed me the movie. The movie was here, actually almost 10 years ago. Nothing special. If you just look at the video, nothing special. The droplet will spread and retract, right, and bounce off. But when I look at the movie, I found something very, very special. Even at that time, the phenomenon is not that obvious, but I saw something special. That it only because of that thing we triggered our breakthrough. So that is when drop try to retract, I see some air pocket. That is totally different from my PhD work. It's totally different from I mentioned. In this current retraction, the liquid contact the solid surface pretty well. But why on this surface we have air pocket? So at that time, I think something is behind. And then because this kind of substrate is not transparent, we can't see the dynamics. So I asked Yahua to fabricate a pillar. The pillar is vertical. We fabricate the pillar based on cutting machine. It's a mechanical tool. In the first try, no, and the first, second, third, fourth, no, fifth, no any good news. At the time, as I mentioned, we don't have budget. I told Yahua, let's try one more time. If still failed, we give up. And in the sixth time, Yahua showed the video I played previously, this video. When I saw this video, I really feel there is a big story behind. So I feel very surprised why in the first try there's no this phenomenon. What happened after 6 experiments? So I asked Yahua to did the SEM. When Yahua showed me this SEM, I feel shocked because at the beginning, our pillar is vertical. Here, there's some magic happening. The magic is after 6 times etching, because every time we make the surface hydrophobic, right? So because the surface hydrophobic, during the etching, the liquid contact top surface. So after 6 etching, so the top surface the space become larger and larger. So this is the reason why we have this kind of tapered structure or pyramid structure. If you ask me to fabricate a tapered copper pillar, actually I don't know how to do that, but that is this kind of failure, which really create the good science. So this is the story behind, and later on, we continue to improve the dynamic weighting by using 3D printing. We can fabricate a robust super hydrophobic surface, and also we studied how the dynamic, how the rotating surface can improve the bouncing dynamics. That published this year. So I briefly discussed the first scientific question. Now let's move to the second one. How make the liquid flow? Right? We want liquid flow faster. We want a liquid flow longer, and we want a liquid flow spontaneously. We don't want to apply any pressure. So that is difficult, right? So our concept is to learn from electronic diode. In electronic diode, that is based on semiconductor, right? Based on silicon. By doping, we can make N-type silicon. We can make a P-type silicon by combine N and P together, and also applying voltage. We have a current flow in one way. So here we can make the topological liquid diode for any liquid, for any material, range from hydrophilic to hydrophobic, even supertrophic to supertrophic. And also we can make this phenomena occurring at low temperature and room temperature at high temperature. More importantly, we didn't apply voltage, we didn't apply force, the liquid flow by itself. So the secret is just to control the surface structure. So by controlling surface structure or surface charge gradient, we can make liquid flow very happily, very spontaneously, and in one way and at high speed at any kind of material, ranging from glass to polymer, to metal. As long as we control the surface morphology, we can control liquid behavior. Okay, so I want to talk about a very, very simple design. In here, we didn't apply pressure. The liquid just flow spontaneously in one way and fast. So that is actually the liquid immediately flow from low temperature to high temperature. That is quite interesting. Usually according to normal flow, the liquid tend to flow from the high temperature to low temperature. But on our surface, we can control the liquid pathway by adjusting control design. We can control different liquid flow. Okay, so actually the design very simple. Now I want to introduce one single unit. Okay, so one single unit here is something like the cell. Okay, this is really cellular physics, right? Focus on one cell. We found here we have the capillary channel. So inside the capillary channel, the liquid flow very, very happily. But the problem is for capillary flow, there's no direction. So the challenge now is how to rectify the flow, right? We want the liquid flow in one way. We don't want liquid flow in other direction, right? So how to do that? In nature, that the spring tail, locally, the surface is hydrophilic. The surface like water very much, but globally, the surface can even repel the oil. The secret lies in the re-entry or the mushroom structure. The mushroom structure increases the energy barrier for liquid penetration. So we just decorate this kind of re-entrance structure to the side wall of the channel as shown here. This just 2 micron design, totally change the liquid spreading landscape. Okay, when the liquid spread forward, for example, in this way, the liquid flow very high. But when the liquid flow back, the liquid is get pinned in the re-entrance. In this case, the flow resistance is dramatically enhanced. Of course, the liquid will flow choosing the pathway with the smallest resistance, right? So by this simple design, liquid can only flow in one way. By contrast, if we don't design the mushroom structure, if the channel is vertical, the liquid will flow symmetrically. So this is very, very simple work showing how we control topological structure can rectify the liquid flow. We call topological liquid diode. And then we can make this topological liquid diode on soft and transparent material. We can make the liquid flow, and also because it's soft and flexible, the surface is robust. Even after several cycles in the cycle, with the liquid still, maintain very good property. Okay, so that is how we control the liquid flow on hydrophilic surface. But on hydrophobic surface is more challenging. The challenge is because on hydrophobic surface, the contact area between liquid and solid is very limited, right? When you drive the car, right? If the contact area is very limited, it's very hard to control your car, right? But there's one very interesting phenomena that done by Fabrication in Duke University. We show that with 2 droplets merged together, the droplet will jump. Okay, so based on that phenomena, and also based on the inspiration from a leaf behind our campus, that here you show the tree in Hong Kong outside our campus. The tree is covered by the leaf, right? If we can look at the needle, the left side is flat, the right side is curved. So this is non-symmetric. Now let's see what happens for condensation droplet or for dew droplet. Okay, so here we show the two forks. The phenomenon is very, very interesting. I show you. Okay, so the first here we have a large droplet, and on the right side we have a small droplet. You know, the Laplace pressure tells us the smaller droplet will be eaten by the large droplet. But on our surface, amazingly, the large droplet is eaten by the small droplet. And also, the left side is flat, the right side is curved. The droplet leaves or droplet flow from the flat surface to curved surface. This is also against to our perception, right? When you, for example, when you climb the mountain, right? You don't want to go to the very dangerous place. You want to go to a flat place, right? On the smooth surface, the energy is smaller, it's safe. But on our surface, we have two interesting phenomena which are against to our perception. So we call this phenomenon tip-induced flipping. This is because in our case, the droplet size is much larger than the tip. Okay, the droplet size is much larger than the needle size. It is because this kind of spatial confinement which change the energy landscape. Okay, and then when we calculate surface energy, the picture is changed. So this explains why we have two phenomena based on one needle, and then we fabricate multiple needles. And you see here that when the droplet first merge, and then the droplet land on the second pillar, and then the droplet will have multiple relay in the air. Because the droplet fly in the air, there's no friction with the ground, and the energy lost is reduced. So the droplet fly very happily at high speed and fly longer. And we're not happy. We make very large scale surface to make the liquid flow, for example, from left to right, to collect water, to collect fog, to produce power. I will discuss later. Okay, so that is based on hydrophobic surface, but on the super hydrophobic surface is more challenge because the droplet on the super hydrophobic is like a hose. It's very hard to control. So how to achieve well-controlled and spontaneous move on the hydrophobic surface? Collaborative with Professor Deng Xu, we tend to drop impact. When drop impact the surface, the charge separation. And then by programming the charge density, we program the attraction force for droplet to move. By controlling the pathway, we can make the droplet to flow along the pathway we programmed. Okay, so now I talk about how to achieve spontaneous, unidirectional, and rapid flow. Now let's look at the history. Okay, so the first paper about the directional flow was published in Science in 1992, right? So over the past 30 years, I lost the paper. But for all this kind of paper, for all this kind of work, so on one surface, all the liquid will flow in the same direction. For example, A flow to the left, B will also flow to the left. If A flow to the right, B also flow to the right. Okay, so it is possible to allow different liquid to flow in different direction on the same surface. This is one scientific question. We have this kind of question a long time ago, but we don't know how to do that because we are not clever enough to design the surface. But one visit to Ocean Park changed our design. So this is the leaf from a plant from a tree in Ocean Park in Hong Kong. My student Shi Lefeng, now he's a professor in Dalian University of Technology. He put it very interestingly. He put ethanol on the surface. The ethanol flow following the ratchet. Right here, you show the manufacturer array. It's really clever. If I do the experiment, I stop there. But he tried another liquid, the water. The water flow against the rapid. So that means on one surface, different liquid can select their spraying direction. But more amazingly, if you look at the structure, the size is some millimeter. We don't have micro or nano structure. But if you look at the capillary velocity, it's very, very rough, very, very rapid. It's even rapider than the structure with nano structure. It's quite amazing. Why the water, flow against the ratchet? Because, on the tip of the ratchet, we have the mushroom structure. Actually, as I mentioned for with another design. So in this special tip, the water gets pinned, and then the water flow against the ratchet. So the work is actually very, very simple. The work was finished 2 years ago, but I didn't write a paper. From my point of view, the work is just enhance our fundamental understanding. So, and then early this year, we write the paper. And also very interestingly, the time also report our result. Okay, so by just controlling the structure, you can control the liquid flow spontaneously and very rapid. And I want to combine our work with recent publication in Nature. Actually, that is from carbon Nature, we call fluid, cellular fluidics. Our design can serve as a cell, a special cell, right? In that paper, we have the cell. The cell is very standard cell, right? So, but on our work, the cell really show the intriguing performance. Okay, by combining our work with the 3D printing, I think, and as demonstrated in the Nature paper, I think a new field of cellular fluidics will emerge. Hopefully, there are some people, will work on this area. So the actually amazing story, should pay a visit to Ocean Park. You see here, this Chinese, right? The cost is $519. That's Hong Kong dollar, actually, only 500 RMB, right? It's very cheap, right? Based on this $500, he got a good paper. Okay, so anyway, I discussed 3 scientific questions. So now let's move forward. The first one is how to fabricate this kind of super hydrophobic surface use a very simple process. Okay, so collaborate with them to publish paper in Nature. We can make the surface very durable. Even after several thousand cycles, the surface still maintain dry and maintain strong. Okay, and today, we can make the surface is super hydrophobic, and also the surface can resist fire, anti-flaming. Okay, and also we developed a 2-stage process to fabricate in large scale. We both we work on the soft photolithography, right? As long as you have template, we can transfer the pattern from the template, the mold, to your final structure. Okay, if you look at the feature here, the feature size is 18 nanometer. Even we have this kind of spiny structure and also the reentrant, we still can replicate the structure for the mold. Okay, if you are interested in that, you can read our paper published 2 years ago. So now I talk about how to leverage on this kind of surface for some application. As mentioned by Richard Smalley, energy and water are top 2 problems faced by mankind for the next 50 years. Right? So if we look at energy, we receive energy from the solar after the first stage transformation, and also after second stage transformation, we have heating, cooling, electricity, right? So today, we have lots of challenge. We still have faced the energy crisis, but in nature, we have lost water, right? We have pretty good technology to efficient energy conversion, but the problem is how to harvest randomly distributed water from, for example, the raindrop, the fog, and also the water flow in river, right? And also, especially in the IoT, we really need clean energy. So actually, this plot was inspired by Professor Wang about some concept from him. Over the past decades, lots of technology have been developed. Right. So the problem is, how to continue to improve the energy conversion efficiency. So I want to talk about from 3 different angles. The first one, is based on solid-liquid interface. Second one, the solid-solid and liquid-liquid interface. By controlling this kind of interface, hopefully, we can improve the energy conversion efficiency. Let's look at what happens when water contact solid surface. Here, we choose Teflon surface because Teflon is slippery and also Teflon carry high density surface charge. But the problem is when water contact Teflon, look like the power generation is not that significant. Why? Because the contact electrification is a surface effect. The amount of charge generated during the contact is very, very limited. We found that when water continue impact on the surface, the charge density can be increased. At one stage, we reach the saturation. Remember, here, we didn't do any work. The work is from the droplet alone. From this point of view, our surface can be treated as a high density source, a source which contains lots of charge, a source we have lots of charge, which is much more than the charge generated during the contact electrification. Now, we answer the first question, right? We have lots of charge. But if you have lots of charge, if you can't release charge, it's useless, right? For example, you earn lots of money, you store your money in the bank, but because of COVID-19, the bank is bankrupt. You can't collect your money when you need it, right? It's still useless, right? So now the problem is after we have lost the charge, how to release the charge? We get inspiration from the transistor. Transistor really represent our society, right? So here we have 3 terminals, source, gate, and drain. Right? So here, when we apply voltage in gate, the electron will flow from a source to drain. So based on this kind of inspiration, we modify the design. We put another electrode on the top of the source. Previously, I mentioned the Teflon can be treated as a source having lots of surface charge. And then, when the water contact the source, nothing happens. The magic happens when water contact the drain. Here, as shown here, when water contact the drain, we have a significant enhancement. Okay, so why we have this improvement? That is because when the drop contact the electrode, the droplet, the source, the drain form a closed loop. This closed loop form a bulk effect, an effect that transform our previously surface effect. This bulk effect fundamentally change the working mechanism of power generation. Okay, more interestingly, when the droplet leaves the surface, and when another droplet comes in, we have another peak. So as shown here, as long as the water continues to impact the surface, we have a continued power generation. So even the paper we published in Nature, we still have lots of hurdles, right? as highlighted in American Physical Society, our work is a combination of two classical phenomena. Actually, I didn't realize our work is a combination of two classical phenomena. The first one is triple electric effect that has 2,006 years history. Another is hydrophobic effect that already have 3,800 years history. Okay, so after our published last year, we continue to improve our work. We integrate, for example, here and here. As shown here, when the water many droplet contact the surface, we have power generation. We can use the power to power the electronic device. Okay. If we don't have continuous water flow, we can encapsulate water inside the tubing. Right? When you move, we can get power generation from the vibration. If we don't have water, we can first collect water from the air. For example, we can first collect water from air, and then we combine the air full collector with our droplet-based electrolyzer. Okay, so I talk about how to produce power from solid liquid interaction. But another important application in marine, right? In marine, we suffer from surface falling. We suffer from hydrodynamic drag. If we can develop a special service, we can prevent the surface falling. We can reduce the drag, and also at the same time, we can generate power. That will be cool, right? So how to do that? I talk at the beginning. So we develop slippery surface based on lubricant. Okay, this surface is very slippery. Even in the freezing temperature, there's no icing and no surface falling. And the hydrodynamic resistance is small. And also at the same time, we can produce power from the liquid.
Zuankai, share your screen, please.
Okay. I think something wrong with my internet, right? Can you see my screen now?
Yes.
Okay.
Yes, we can see. Yeah.
Okay, sorry, because I'm in hotel, the internet is not very stable. Okay, so let's continue. Okay. Even for solid interface, we can, as long as use our transistor-inspired design, we can significantly enhance the power generation. For example, we can achieve power density up to 10 megawatts per square meters. Okay. So as summarized here, our design is generic. We can harvest energy from water, from droplet, from moisture, from continuous water flow, from small scale to large scale to open system to closed system, from solid interaction to solid liquid interaction to liquid interaction. And also, I want to talk about the thermal management, because as mentioned by Ren Zhengfei, thermal is one of the biggest challenges for Huawei, right? We put more and more transistor on the computer. A computer is very sad, right? Don't make me so hard, make me cool. So how to cool down computer? Right? So we use phase change. But there's a fundamental problem. That problem is at high temperature, and the water evaporate, they form the uniform vapor layer. This vapor layer will block heat transfer. So that is the reason why the nuclear power plant disaster happened in Japan 10 years ago, right? By controlling the surface structure, still it's very hard to prevent, this kind of phenomenon. Okay, over the past 200 years, a lot of progress has been done to suppress this phenomenon. But today, we solve this problem. Actually, I first talk about our work done several years ago. In this work, we didn't successfully solve this problem. So we want the liquid flow from a Latin force region to boiling region, because the boiling region is what we want. The boiling region has a very good heat transfer, right? So we just fabricate the surface with structure gradient. But today, as shown here, this our design, the surface temperature is 1000. When the water contact the surface, immediately the surface will be cooled down from 1000 degree to below 100 degree. But on the control surface, no matter how you apply water, the surface couldn't be being cooled down. The surface maintain the high temperature. Hopefully, our design can change the heat transfer landscape. And also not only in open space, we also fabricate a microchannel based on the flow boiling that is collaborated with Wang and also Chen Li. And as shown here in microchannel, we have a hydrophilic pillar, right? So when the water gets evaporated, the capillary effect will refresh the water, and then we prevent the film boiling. Right? In this case, we have efficient heat transfer. This kind of device can be used for electronic cooling. And also, this is the work done by my first PhD student, Xue Mei. At that time, okay, so we really have trouble to publish the paper, because at that time, we don't have very good understanding at the beginning. So the story is, we want hydrophilic surface for very, very good nucleation. But also at the same time, we want super hydrophobic surface to make the water flow away. Otherwise, the surface will be covered by water. So finally, after 1 or 2 years collaboration with Zuankai in UFT, we designed this hybrid surface. The sidewall is hydrophobic for good nucleation. Globally, it's super hydrophobic for very efficient departure. So by this way, we solve the condensation problem. And today, also we work on reduced cooling, because the reduced cooling is very good passive cooling, right? So our purpose is to send the heat to the outside space, because outside space, the temperature extremely low. It's only 3K based on second law thermodynamics. If we have a large temperature difference, the heat transfer efficiency will be much higher. Like over the past several years, lots of work done in this area. The key is how to control the structure to reduce the solar absorption, but at the same time to enhance the reduced cooling. And also collaborated with Professor Xue in Xi'an, Shanxi province. We developed the super hydrophobic reducing cooling, the coating. The coating is durable, right? And we can have temperature drop by 5 or to 8 degrees. We don't have any energy input. Okay, so in our lab, we also work on other applications. For example, adhesion. Adhesion is very close to wedging, right? Usually we use double-sided tape, but the problem is when we put the double-sided tape in water, we don't have very good adhesion. We learn from a gecko, but also gecko doesn't function well in water. And then we turn to the mussel, right? So mussel have very good underwater adhesion, but the problem is how to achieve reversible underwater adhesion. So several years ago, we proposed a new concept of reversible underwater adhesive. Very, very simple. We just control the temperature, and then we can switch the adhesion. And today, we continue to use capillary adhesive. We can achieve, the reversible adhesion, and also even on the tapered surface, on the curved surface, we have reversible adhesion. So this kind of adhesion can be used to manipulate object in marine. Okay, and also we develop flexible electronics to have very good adhesion and also very good optical transparency and also very good sensing function. For example, we can sense the temperature, we can sense the pressure, and also we can use 3D to control the morphology. Here, we work on the solid state conductive elastomer, and by use DLP printing, we can change the control the morphology, right? As shown here, by controlling the different morphology, we can increase the detection sensitivity. Okay, so I think this part. So I use maybe how much time I use 15 minutes to cover lots of work done in my lab. Sorry, this is in Chinese. Okay, so my talk is focused on surveys. But the most important is how to learn from nature to develop highly integrated, highly smart, and intelligent and self-healing material. Because for human being, right, we have the best function. So in our lab, we just start. So I think there's a long pathway to go. Hopefully, maybe in the next decade, we can achieve some milestone or make more accomplishment to share with you. Okay, so finally, I want to thank my team for their hard work, my collaborator over the world and funding support, and also all the audience online. Thank you very much.
Thank you, Professor Wang, for such a fascinating talk. I think before we move into the panel discussion, we've got 2 questions from the audience. So I will just read the question and probably you can address the question first and then we'll move to the panel. Okay. So the first question is that Professor Wang, wonderful work. I want to know that do you have any real application examples of this super micro nano surface? So perhaps, I think you have touched on some, perhaps give a few more examples, if possible.
Okay. It's very good question. It's always good to connect basic research to practical application. So for one application, as I show here, these are our device, actually that we call the armor for heat transfer. Actually, I mentioned that today we can completely suppress the Latin frost. Right? Latin frost is a classical challenge which bothered us for over 200 years. So here we design this kind of not nanostructure, it's just a microstructure.
Sorry, Professor Wang, can you talk a little bit closer to your speaker because we can't hear you?
Oh, you cannot hear. Oh, sorry. Okay. Yeah. So it's always good to connect basic research with practical application. As shown here is our device for thermal management, right? This one, even the surface is have temperature more than 1,000, right? When the water contact the surface, we can cool down. The surface, as shown here. At the beginning, the temperature is 1,000 degrees, and when water contact the microstructure, we have efficient thermal cooling. The temperature will fall below 100. So that is one application I think has promising application.
Thank you. Our second question is from Boli from Xi'an Jiao Tong University. He would like to know if the specified nano surface is applied to selected liquid material. Or
yes.
Velocity only. Yeah.
Yeah. Yes. The liquid behavior is very important. It's very important. Right? So, for example, the different surfactation and viscosity. But for our work, we most work is focused on the liquid. So in that case, we don't care about viscosity. Usually, in our most of our application is dominated by capillary effect. In that case, the viscous or gravity not important. So we care about the surfactation effect.
Okay, thank you very much, Professor Zuankai Wang. So now we will move to our panel discussion. So before we start, let me first introduce our panelists. The first panelist is Professor Tie Li, who is a distinguished professor of Shanghai Institute of Microsystem and Information Technology. He is also the Vice Director of Science and Technology on Microsystem Laboratory. Professor Li's research interests include design, fabrication, and application of micro and nano sensors. Certainly, Professor Li has published many research papers, including 180 papers, 67 Chinese patents, 2 US patents, and 1 Japanese patent. He also received many awards from various sources. Our next panelist is Professor Anderson Sum. He's from the Department of Mechanical Engineering and Biomedical Engineering Program, the University of Hong Kong. And he's also director of the Advanced Biomedical Instrumentation Center. Professor Sum's research interests include emulsions and biofluidics, biomedical engineering, and soft matter. Professor Sum has received many prestigious awards, which I'm not going to read it out because it's too long the list. But he also is associate editor of and also editorial members for many international journals. My next panelist is Dr. Yin Ling. She's also the ex-challenger, I think, of our panel tonight. She is currently a postdoc scholar in Professor Thomson's lab in the Department of Radiology at Stanford University. And she did her bachelor degree from UC Berkeley in 2014, and then continued her PhD under the supervision of Professor Ali Javi, also at Berkeley. She has published many papers in Nature, NatureCom, Nature Nanotech, and very many top journals. And also she's a recipient of Innovators Under 35 Asian Pacific 2021. Her research interest is about using materials and DNA technology and to integrate them into devices to detect biosignals in complex biofluid media. So without further ado, let's just join our panelists to start ask Professor Wang questions. We'll start from Yiling as ex-challenger, please.
Okay, thank you very much for your introduction. And Professor Wang, your talk was fantastic. I really enjoyed a lot of, especially with the videos. I think it's really easy to understand and it makes the whole talk like a lot more interesting. So I have a question, which is more on like the fluid transport. Since I work with a lot of like biofluids, so I was just curious. So if we look at the more realistic application for the fluid, like the water transport, instead of looking at like water, if we're looking at more complex, like not very clean water or like even biofluids, how the water transport can be affected. And what do you think if we want it to work in a realistic application, how do you foresee the main challenge that we should first address?
Okay, I think thank you very much for your very positive comments, and I think this is really a touch question, which we think several years, because I also have some 1 year training in biomedical engineering. Right? So, but if we look at this area, we do have some connection between the surface with biomedical. We over the past several years, there are there are some extensive progress on engineering surface which can repel the bifluid. For example, the super hydrophobic surface can repel the blood or repel the protein. But in the longer time scale, this effect disappear. Because the protein can still attach on the surface. So I think this kind of challenge remain, right? So that is on the super hydrophobic surface. On hydrophilic surface, I think the transport is not a problem. So for the PDM channel, right? I think nothing special. But I totally agree. How to move forward by addressing the biomedical and also very complicated bifluid problem.
And maybe I have one more question is for these nano features, I know you mentioned like it doesn't matter what kind of materials it is. So like I think it's just amazing to me. So if you use like either like some like metals or like polymers or any types, so the for these it's the fluid behavior is all the same, or it will have some influence.
Okay, thank you very much for giving me the chance to clarify our design. Because of time limit, I didn't mention the material used. I only focused on surface structure. But it is true that the material property, for example, is also very important. But that is really depending on application, right? For example, for thermal application, we tend to use thermally conductive material, right? But for conventional liquid transport, probably that's not important. But for maybe also for electrical power generation, right? That one you also have to choose some very good material. For example, you choose Teflon because that Teflon has very good permanent surcharge. So I think the material substrate is really based on your application. For different application, you choose different material substrate. Yeah.
Okay. Thank you.
Thank you.
Thank you very much. I can now accept questions from other panelists.
Okay.
Yes.
Right.
Yeah, go ahead.
Okay. Zuankai, you just gave a very wonderful talk, and I do enjoy your talk. And I'm also very proud of you because you got graduate from our institute.
Thank you, Professor Lee. Yeah.
Okay. And just in your talk, I learned you have investigate the surface of materials. And I think the most important thing is the material as well as the structure of the surface.
Yeah.
And I just learned the structure of the surface is so complex, right? And when you control the structure, when the surface is controlled in your way, you can control the property of the surface.
Yeah.
And my question is, how could you control the surface in micro and nano scale? And is it possible to make mass production?
Okay. So thank you very much, Professor Lee. I want to take advantage of this opportunity to express my great gratitude to you. Okay, I really enjoy the time in Shanghai back to almost 20 years ago. Okay, so the question is really regarding the microfabrication. I totally agree. Microfabrication is essential, for our surface design. But the good thing is for our application, because the liquid here there's one feature size. That feature size is the capillary length. So usually capillary length is roughly 2 millimeter, right? So by seeing that, so we don't have to use a well-defined structure, right? So as long as the surface is rough, we can make the surface super hydrophobic, unless you really want to control the liquid flow. So, for example, we also fabricate reentrant, right, structure to make the surface super hydrophobic. Yeah, and actually, this kind of fabrication is really not that demanding. We just use MEMS technology or even machine cutting and also some wet etching to fabricate. And for large scale fabrication, we also develop some robust technique. For example, we discussed we discussed that I think it show here. Oh, okay, not here. We discussed the two-stage soft photolithography. For that technique, we can replicate the surface very easily from the mold to any kind of surface. And also, we rely on spray coating, right? So we can just use spray coating, to fabricate the surface. Okay, so that is my answer.
Okay, thank you.
Thank you.
Okay, Professor Song, you have questions, please?
Yeah, so thanks a lot, Zuankai. I think it's really amazing what you have done with all these, starting from the physics and also the bio-inspired structures and all the surfaces with such precision and reproducibility, etc. So I have a few questions. So my first question is, because you do have to do very delicate control of the surface. So what would be your suggestions on how to do this over a really large area so that they will achieve all the same effects? And in terms of the cost analysis, how competitive would the cost of these be in terms of if we have to implement all these services over a very large scale? And my third question is, if obviously many of these are bio-inspired at the beginning, and then so the structure is bio-inspired. Would there be some ways to also take inspirations from biology or from the nature to fabricate these structures as well? So these are the three questions that I have.
Okay, thank you very much, Anderson. So I think the question also related with fabrication. We made some progress in scalable fabrication. For example, here we show how to manufacturing the micro nanostructure use the two-stage photolithography, right? If you look at here, the pattern, the feature size is very small, and as long as you can fabricate the mold in large scale, we can just transfer the pattern from our mold. That is very powerful. It's very easy to be done. And also, as I mentioned, the capillary size to just achieve the super hydrophobic property. We don't. The structure is not that sensitive or not that depend on the specific feature of the structure. For example, even we use the spin coating, we still can maintain very good super hydrophobic property, right? So even for I mentioned this kind of directional flow, right? So that one can be achieved by a very simple 3D printing. Okay, so I think in one word, because the liquid, the capillary length is large. The capillary length is 2 millimeter. So by this way, we can release the requirement on the feature size. Okay, so and also for you mentioned the biological inspired fabrication. I think that is really a good direction for us to go. So by inspired design, but so far our work haven't reached that stage. But hopefully, we can move forward to that direction. How to fabricate self-healing and functional soft material, which really sustain in different working environment, even inside of the body. But I think there lots of room. Yeah.
Thanks a lot for your answers.
Okay, thank you.
So before I move to another round of questions, perhaps I will also ask a question. So as a person being working with semiconductors, I just wonder if you have been working, also have some experience in actually dealing with the semiconductor substrate and probably using 3D printing or some fabrication to achieve some surface control. If you could give us an example, that would be great.
Okay, so we do use silicon, for many surfaces, we fabricate on silicon because silicon is still the best material to achieve good pattern. So for example, our liquid diode was fabricated on silicon, right? For other, for example, other semiconductor material, for example, silicon carbon, we don't work on that because we don't know how to fabricate how to achieve the good pattern for that. Yeah. But because so far our work and also our application is still focused on thermal and for the power generation. So the material is very common, just based on the polymer and copper and steel, aluminum. Yeah.
Thank you. And I also have a question about so you've shown so many beautiful, bio or nature-inspired design. Also, I'm sure it looks easy, but in terms of to real translate a basic concept and idea into a working device or demonstration, that's a lot of challenge. And can you actually give some sort of example? What is the biggest challenge you think? Is that really to come up what is actually the theory behind all this design?
Okay, this challenge is a kind of challenge. It's true, first, if you just look at the design, it looks like simple, right? But underneath the simple design actually lie very deep physics. Okay, so we do need very good understanding to have better function. For example, the liquid diode I mentioned here, how to rectify the liquid flow. Okay, so we take a longer time for us to come out with this elegant design, right? I think the design is quite beautiful. If you look, just replicate one unit, right? You can make the device. It's very simple, but here, for example, here we have the capillary channel, to have a rapid liquid flow, and also we have the re-entrance structure to get liquid pinned at here. So as a result, the liquid can only flow in one way. And also for our thermal management, as I mentioned, we solve a big challenge in thermal engineering. That one is a challenge which already lasts 200 years. So our design is also, just look at the design, also simple, but not easy to reach that stage, because in that extreme condition, you have hot temperature up to 1000 degrees, right? You have water flow, you have vapor flow, right? And also you have the material, you have to consider, the stress. Okay, how to come out one design which can control the vapor flow, control the liquid flow, make the material to sustain the high temperature, make the surface can be fabricated into good pattern, right? So all this challenge, all this design should be converted together. So that in that sense, okay, it's not that simple. Even it's just on surface, and I think a deep understanding is there. So I totally perfect. So I think I totally agree. Okay, so that's not easy. Yeah. Oh, I can't hear you, Professor Fu. You unmute yourself.
Sorry, I somehow didn't unmute. So do we have any further question? We do have another 5 to 10 minutes time, so please do follow up.
Maybe I can ask one more.
Yes,
if
please
time
go ahead.
allows.
Yes,
So
go
I
ahead.
think, I think we also have a lot of students and young researchers among the audience. The question that I'd like to ask is, how do you get to see beyond just the superficial side of the science and be able to think so deeply about how some of these structures may have in terms of surprising features and implications on the actual functions? I think that is a very important and valuable things for young scientists to learn about.
Okay, Anthony, I think it's a very good question. I think the first one I want to answer this way. I always tell my students it's very important to look at milestone, right? For example, here I show the milestone in our research area. We first know the history, and then we realize where we are, right? Which kind of question already being addressed, which kind of question remain unknown, and after we have a clear picture, and then we start to formulate some question. That is most important, I think, for young researcher. But the better thing, is in the information technology, in the making society, in current society, every day we receive lots of information bombarded to our head, right? We don't have time to think. Okay, it's good to be calm, to slow down, right? To slow down, okay, to read the history, to know where you are, right? That is the first step. The second step, I think, the second thing I think is very important is to be proactive, to be proactive, to be patient. After several hundred years scientific research, not so many things which are totally new, which are totally exciting. If we always dream, okay, I want to do something with challenge, but we never put into action. That's bad. Only have a vision without action is daydreaming, right? So on one hand, we need vision, but on the other hand, probably action is much more important, right? If we have good action, and in this kind of action, probably we can encounter some surprise. For example, as I show here, after 5 times failure, if my student never tried the 6th time, we missed the pancake bouncing. So I think this is the good lesson for the young students. Most students, okay, Professor, I did this experiment, it failed. Oh, that's it. They never try the 2nd time, the 3rd time. When you fail, you should think, oh, this is positive. Okay, if you think your first try is positive, it's not that important. Actually, it's superficial, right? The good thing only will come after you suffer. After you suffer from pain. Okay, I think that's my philosophy. Yeah.
Thank you very much. So I think we learned that in order to be a great scientist, we also have to first be a historian of our own area and topic.
Yeah.
Thank you.
Very good point indeed. I think also persistence is very important for anyone doing science, I guess.
Yeah.
Professor Lee, do you have any further questions?
Okay, my questions. Is it possible for you to give us talk in Shanghai in our institute?
Perfectly. I always want to go back to Shanghai because I treat Shanghai as my another hometown. Okay. Hopefully, I can go there. Maybe this year probably not possible. COVID. Now the situation in Shanghai. I think there's a new case right in Shanghai today, right? Today. Okay.
You're right.
That's
Maybe not this time, but
okay.
Yeah.
Good.
Okay.
I really wish I can go back to see you in person. Okay.
Okay.
I'm sure after your beautiful talk today, you will get more and more invitations. So, Yiling, do you have any more questions? Burning questions?
No, I don't have further questions. Thank you.
Okay, so if we do, because we do have some announcement to do after this talk, so we probably can wrap up a little bit earlier. So let me just thank Professor Zuankai Wang again for a really, really interesting, inspiring talk, and also thanks to our wonderful panelists for a very, very interesting discussion. Now I would like to invite Alice back to the floor to award the certificate to Professor Wang.
Okay, thank you very much, and it's so great to hear all these discussions and the wonderful talk as Zuankai always delivered. So Zuankai, you got a lot of questions online. Actually, I couldn't read all of them. I suggest you go to the website and answer all the questions because many people. Yeah, like Lan says that they really, love your talk. You will get more invitation. But first to answer all the questions, okay? Yeah. So for now my job is to deliver this certification to you. Yeah, because I can ask, I see that, so every time, yeah, we have these special certifications for our speakers. So, Zuankai this time, yeah, deliver to you for SOS. Yeah, surprise on service. I think that's a very good title, and also, of course, yeah. So welcome you, to deliver a talk, and next time, yeah, to share your wonderful research.
Thank you, Professor.
Okay, cool. Yeah, today we really have a lot of things to announce. Zuankai here, we see that, Zuankai young scientists, and this time we invited all the young scientists to join that. So because we will announce our ICANX Young Scientist Award, the finalists. Actually, we have a very strong committee. Me, Fu Lan, yeah, the moderator he just now here, and Paul Weiss, Yuri, Gogotish, so our, I can ask talks several times, and Jürgen Brugger, my friends in EPFL, and Miso, everyone know her, our lovely lady last year delivered talks very good, and Martin Suo was our co-hoster this year, and Martin was a young scientist winner too last year. He won the ACS Rising Stars. So we have these committees. We got a lot of candidates. We have 47 candidates from 15 countries and regions. See this map, I love it very much because see that we have almost from the whole world. We have from Australia, we have from Singapore, we have from Japan, Korea, China, and Hong Kong. And we also get several candidates from India, and we have some from Europe, like UK, Spain, and Italy. And it's amazing that we don't surprised we have candidates from United States, but we are really surprised we have candidates from Africa. Yeah, so we got several very good candidates from different parts of Africa. They done very good research. So this time that's the totally candidate, and 11 of them are young ladies. Yeah, I'm so proud of that. Even the young ladies from Africa, they really contributed the best, best the work and the results. So after a hard work by the committee members, now we come out to announce that the shortlist, finalists of 2021 ICAX Young Scientist Awards. Its order was in the last name, so I will announce one by one. Xian Ding was from Shanghai Jiao Tong University, China, and Jesse Gitaka, also from Mount Kenya University, Kenya from Africa. Africa. And Shi Wen-gong was from University of Michigan Amber, from USA. And Deep Jariwala was from University of Pennsylvania, was from USA too. And the next one is Sante Kim, was Hanyang University, Korea. And the next one is another Kim, is a lady. Sinjung Kim was from University of Melbourne, was from Australia. And we have a Harvard Lee from University of California, Urban, was USA. We have another Lee, is Deng Yuan Lee, was from City University of Hong Kong. It's a colleague of Professor Zuankai Wang, also from Hong Kong. And we have another one, is Araka Majumada, University of Washington, Seattle, USA. We have Xin Qian from Huazhong University of Science and Technology, China. We have I hope I can read it correctly. Cameron Esperanza Sandria was from Spain. The university name, University of Basque Country, UPV or EHU. So if I pronounce not that correctly, please next time teach me. And Hai Ding Sun, also from University of Science and Technology of China. We have Tang Wei, was from Beijing Institute of Nanoenergy and Nanosystem, Chinese Academy of Science, China. And we have Flavia Vitali, was the University of Pennsylvania, USA. We have Fan Wang, was from University of Technology, Sydney, Australia. We have Si Hong Wang, was from University of Chicago and USA. We have Marisa Vetchersler, was from University of Texas and San Antonio. And we have Zhigang Wu, was from Harbin Institute of Technology, China. We have Xie Xi from Sanyishan University, China. We have Tomoyuki Yukita, was from University of Tokyo. We have the last one is Long Zhang, was from Xiamen University, China. So that's all we have, 21 finalists. And congratulations to all of you. Actually, it's very hard job to choose, to select it. But thanks to all of you, your best contributions. And this time you get the final chance, to get on the stage. For the final defense will be online. ICAX, that's a schedule. Next week, we will do the draw loss for the final defense orders after the ICAX talks. And then we will do rehearsal the week after. And the final defense will be two groups. The first group will be December 16, and the second group will be December 17. So each finalist will have 80 minutes, 15 minutes presentation plus 3-minute question and Q&A. As the top 10 will be awarded on the award ceremony and December 17, the last day of ICAX talks this year. So that will be a big ceremony. I hope all of you be ready here. And next week, we will have a wonderful ICAX talks with from Pupa Gilbert. Pupa was very, very nice work. If you want to know more about biomineralization, that means you want to, dig out how these dinosaurs, the teeth, the peers, how the structures and how it, formed that way. So Pupa will tell you the story and all the details. So it will be a wonderful talk. And after the talk, all the finalists, please join. We will do the draw lots online. So that's all this week, and be sure stay with us on ICANX. So see you next week, next Friday. Bye.